Okay, now I'm going to prove the second part of the fundamental theorem of calculus. So, we want to keep in mind that the first part of the fundamental theorem of calculus says that I've got this f of x is equal to some integral from 0 to x of little f of u du, and actually it's not from 0, it's from a, just from some constant to x. Okay. Well, the first part says that f prime of x is equal to f of x. So this tells me that big F of x is an antiderivative of little f. Antiderivative. Oops. Of little f of x. Okay. So now let's suppose, so that's just a statement, we know that. Right. Okay. So now we're going to choose another function. But actually we're going to choose the same function, we're going to give it a different name. I'm going to say g of x, let g of x be this integral from a to x of f of u du, and then we also want to let big F of x be another antiderivative of little f of x. So I know g of x is an antiderivative, I know f of x is an antiderivative. Now that means that they differ by some constant. Right. So g of x, we'll say it's equal to f of x plus some constant. Okay. Well, now I want to look at g of a. Well, g of a, so I define g as this integral here. So I'm just going to plug in a where I see x. So g of a is equal to the integral from a to a of f of u du. And it doesn't really matter what f is. If you take an integral from something to itself, you're integrating over an interval that has no length. You're integrating on a point. So that has 0. There's no area under the curve at a point. So, and that's something we should know. So that's g of a. Well, I know g of a, so I know g of x is equal to f of x plus c. So that must mean that this is equal to f of a plus c. But I also know, well, that means f of a plus c equals 0. This tells me that c must be equal to negative f of a. Okay. So remember, f of x is just some antiderivative. I don't know what its value is, but I know whenever I plug in a, it has to be 0, which means the constant over here has to be negative f of a. And so f of a is just a constant because it's f evaluated at one specific point. Great. So that means that the integral from a to x of f of u du is equal to g of x, which is actually just f of x minus f of a. And all that remains to complete the proof is say, well, let x equal b. So the derivative from a to b of f of u du is equal to f of b minus f of a, where big F is just some antiderivative of f of u. They all differ by a constant. And, well, hey, there it is. The second part of the fundamental theorem of calculus.